All right, guys, let us review what we did so far. Last time we did two things. We did, if you remember, we did boosting and we did a little bit of the recommender system, or at least we got started with the recommender system. The main point with boosting was, and we in particular took gradient boosting as an example. Boosting is a process of creating a strong learner using weak learners in a way that you learn slowly. You take a weak learner, you fit it to data, you see what mistakes remain when it makes the prediction. In the case of a regression problem, for example, you take the errors from a model so far, and then you use it to build another model, another weak learner, whose job is to be able to improve upon the model by just fitting to the errors. Right? So if you look at the screen, we said that we have the overall model is built out of pieces. It is built out of, let's say that any given level, you take the model that you have built so far, and then you add one more model to it, one more weak learner to it, that is fitting to the residuals, for example, in regression, residuals left behind by the previous model, right? And you attach a damping factor so that it doesn't go and overfit, but broadly speaking, that's what you do. So the first model that you build, like the zeroth model that you build, is as simple as it can be. It is simply basically a baseline class, a baseline regressor. It says that ignores all the predictors. It says that the predicted value is the average of the learning data target value, right? All the labels, all the target values that you get in the training data, you just average it, and that's your prediction. Well, it is a very weak predictor, but at least it makes sense. If you have no inputs, the best that you can do is predict the average. You do. Then what do you do? Next, what you do is, so that is the prediction from the zeroth model. You look at the residuals that you're left with, yi minus y bar, that becomes the residuals. And thereafter, you try to fit a function to the residuals. When you fit a function to the residuals, a learner to the residuals, that's what your learner is. Now your learner, quite often people in boosting, they tend to use decision trees, but it need not be. You could use whatever you want. If you use that and fit it, notice that you're not fitting it to the Y, the actual labels. You're instead fitting it to the residuals from the zeroth model. You will get another model now, F1, a decision tree, let us say, for F1, a weak learner for F1. Now you have F0 and F1. You would put it together, F0 and F1, to get the overall big model, which is F0 plus F1 up to a damping factor. What will that model do? That model will now make predictions. Once it makes predictions, it will have its own errors, own predictions. Those predictions will have its own errors. And those errors now you'll fit to F2. And you will keep on going up to a certain extent. You can choose m is equal to 20 or 30, or whatever it is, 100. You can keep on going sequentially, building an ensemble with weak learners. Are we together, guys, so far? This is the basic idea that we said we are pursuing. Now, with this basic idea, when we apply it in practice, as you will see today, it becomes quite simple. This is the gradient boosting. It's accelerated version, massively parallelized, and optimized version is XGBoost. These things work very, very well. Now, that was the process of boosting, which is different from bootstrapping or bagging. Bagging is bootstrapping and aggregation, simple aggregation. In bagging, the advantage is you can build models in a massively parallel way. So for example, when you're doing parallel computing, if you look at big data frameworks like Spark, for example, you look at the history of Spark's machine learning library, MLlib, and you realize that they had random forest ever since the early days of machine learning, early days of Spark, sorry. In one of its earlier implementations, they already had random forest. Why? Random forest is very in a way, in many ways, straightforward to parallelize. Right? You grow a lot of trees in parallel on bootstrap samples of the data, and then you can do SGD, stochastic gradient descent of some form, and you do have the implementation essentially in place. Boosting is a little bit more tricky. How do you do sequential on a massively, like how do you get a parallelism or distributed computing when you are dealing with something like boosting? It's a little trickier. And you can see that it showed up in a framework like Spark after considerable time. It showed up. So then people worked hard and they figured it out actually. Some very clever fellow figured out how to do, this is the extreme gradient boosting, how to do a parallelized implementation of it. And then now people have tried to do more of it. They have put it on GPU. GPUs are extremely good with parallelized computing or distributed, this sort of a divide and conquer approach. And for example, Cat Boost, another variant of it, and very, very good variant. It can run on your GPU, your video cards, or GPU. There's GPUs and R. If you can push a computation onto GPU, a machine learning computation onto a GPU, you clearly have a winner, because GPUs do matrix manipulation orders of magnitude faster, sometimes hundreds of times faster than the most powerful workstation grade general purpose processor. Like for example, Intel Xeon versus GPU, or whichever GPU. So let's say commonly in the data science machine learning AI world, you tend to use NVIDIA. I don't know why others haven't caught up yet, but NVIDIA is very, very popular. So you take a typical GPU like RTX 6000. It's pricey. RTX 6000 or RTX 8000 will easily set you behind $4,000 or $6,000 or $8,000. So these are not a small change, but the computational benefit it will give you is almost 100x acceleration over your typical Xeon processor. Now, the Xeon processor is a general purpose processor. It can do very complicated instructions, whereas the computations on the GPU are very, very simple in many ways. They're multiplication of matrices and so on and so forth. But for the things that the GPUs do, they do very, very well. So now there are implementations of these things on the GPUs. Of course, our whole next bootcamp, the TensorFlow, is all about GPU computing. We'll see, deep learning. We'll do it using PyTorch principally, actually. TensorFlow also we will do, but not to as an extent. PyTorch is more like beginning to feel more natural. If you have been doing NumPy, which we all have been doing in the first and the second workshop, PyTorch is almost a no-brainer with very little learning curve. You become familiar with it. And that is its great power. It's very expressive, very simple framework. TensorFlow is quite powerful and has an equal mind share, but it certainly feels like a quite different metaphor for programming compared to NumPy and so forth. So anyway, we'll come to all of that in the next. So besides bagging and boosting, what else do we have? We have stacking. Stacking is taking some really you have tuned algorithms. You go and train your independent learners. If you so want, you can even take some strong learners though. And then what you can do, you can stack them. You can create a last level learner here. What does the last level learner do? It treats the predictions of each of the learners as its input and says, can I see a pattern in the way they're predicting and the strengths and weaknesses in the prediction? Maybe some learner is predicting well in some region and not in other regions of the feature space. So can I do a further learning on the learners themselves? And when you do that and then make a final prediction, the most obvious example would be just a linear combination, just some weighted combination of the predictions of the other learners. Giving more weightage to a learner, you trust more, and less weightage to another learner, and so forth. You could do that. For regression, for classification, you can do some sort of a sigmoid of that. But More and more, what is common is not to do something linear, but to use one of the more powerful, like a really powerful algorithm at the tail end of it. And what you put there typically is a SVM or a neural network. Right? You put a few layers of a neural network, or sometimes just one layer of a neural network. And we find that you can sometimes, not always, sometimes get pretty good prediction from the sum total of all of it. So this is called stacking. Are we together? Now, stacking is, of course, much more sophisticated. A lesser version is just a voting classifier. Voting classifier just says you create an ensemble, but you make it out of all sorts of different algorithms. You still do a committee, a jury, or a voting, but one may be a decision tree, one may be a support vector machine, one may be something XGBoost, one may be logistic regression, and one may be a LDA or a QDA, and so on and so forth. And you take a whole bunch of classifiers and you just take a direct vote. So that would be the equivalent of saying a voting classifier is the equivalent of saying that all of these votes, these weights are essentially one, right? And you're just taking the average of them, or rather 1 over n, n being the number of classifiers you have in your model. And so you're just taking a direct average of these. So that's a voting classifier. You're essentially bagging the response, the predictions from each of them. Now, so we learned 3 ensemble methods. We learned bagging. One example of this is random forest. And then the extremely randomized trees and so forth, etc. I won't write all of them. And boosting. We can do gradient boosting. As I said, AdaBoost, I didn't emphasize too much. What AdaBoost does is it takes a slightly different approach. It grows a tree, and then the mistakes are amplified to build the next tree, and so forth. So you keep on composing, but by amplifying the mistakes. I didn't go too much into the detail. It's usually other people would perhaps start by teaching AdaBoost first and then doing it. But I thought because gradient boosting is so very dominant these days, let me stay with the main one. But okay, there it is, AdaBoost, and XG. XGBoost is essentially just a very fast implementation, fast gradient boosting. Right? And then there are other variants of it, like for example, CatBoost. I believe, Dennis, you used CatBoost and got pretty good result on your Higgs boson, isn't it?
It is a very strong classifier.
It's a very strong classifier. So just to give you a perspective, the project that Dennis took up was the Higgs boson, and he's already getting a pretty good accuracy of 83%, isn't it? 83, 84?
I'm looking at 84.
84, excellent. Yeah. Which is the state of the art, isn't it? The leaderboard is at 84.
The measurement is actually called the approximate median significance that has its own formula, but you know, and 84 is pretty good, yeah.
Pretty good. Huh? What is the highest there?
For EMS, it's like 3.8 or something.
Okay.
Yeah, like I'm not sure about accuracy though.
Okay. All right, so here we are. Then after this, we did another topic. So today our lab is on boosting. We won't get time to do the recommender system lab. That is actually part of the math course. I will do it there. The recommender system was based on the idea that you can do user-user similarity or item-item similarity. But sometimes just by observing users engaging with items, either listening to music or watching movies or buying things on an e-commerce site, by just looking at the interaction matrix here, you can look at the interaction. That is transactional data. Maybe in some database it says that this user bought this thing. Out of that data, you can create a matrix, the matrix of the user interaction with items. this user bought this and this item, and maybe gave this rating for a movie or a song or something like that. Based on those things, you can ask a question, you can make a hypothesis that the items have certain traits and the user has certain taste for those traits. And can we find that low dimensional representation? Here, obviously, we took an absurdly low dimension, a 2 dimension. We said movie can be a thriller or not, and it could be humorous or not. And so we put all the movies somewhere on the spectrum. 2 dimensions are obviously absurdly low. They don't capture all the sort of traits of a movie, but it sort of illustrates the point. So every item can be projected into the space, and then every user can be projected into the space based on their taste. So items have traits and people have taste. Okay? And so you can see that there's a person who will like Sleepless in Seattle quite a bit because of their uh, choice of a certain degree of humor and a certain action thriller, like the level of action they want to see in that. Okay? So this is the main concept. Now, the hypothesis that you make is that if you represent a user, the taste of a user, the degree of taste for each of the traits, you can represent it as a vector. Those are the attributes of each user, how much taste a user has for humor, for action thriller, for, let's say this is action thriller, this is a humor, and so forth. And likewise, every item can be represented with as a column vector, saying how much of humor, action thriller it has and how much of humor it has. And therefore, the inner product could be thought of as, the cosine could be thought of as a good indicator, a pretty good indicator of how much a user is likely to uh, resonate with a certain item. Right? So this space, this hidden space of taste or traits that you say, the more formal word mathematicians use is latent space. Latent means hidden. See, your matrix is the obvious data. This is transactional data. If you look at it, this is transactional data. But you're hypothesizing that the reason people buy things or engage with certain items or watch certain movies is because items have certain traits and users have certain degree of taste for each of those traits. And so you have a latent space, not just 2 dimensions, but typically 10 or 20 dimensions or 100 or 200 dimensions, which are true representative of the item. It is that which is not there in the description of the item, right? But it is something more abstract. And that emerges, that pattern emerges only when you look at a lot of interaction data. And how do you go find it? There are methods like alternating least squares, and we do singular value decomposition and so forth. And when you do that, you're able to pinpoint a user in the latent feature space, and you're able to pinpoint an item in the latent feature space. Then you can look at similar items in that space. You can look at similar users in that space. You can recommend items to a user by looking at what items surround the user. You can look at users to whom you would like to sell the item by seeing what users surround an item. So you can run a campaign from a marketing perspective to sort of advertise those items to those users, recommend those users to buy this item with perhaps greater degree of success than just brute force broadcast advertising. So that is the world of personalized advertising. Uh, that's where it comes from. That's where the personalized ads come from. So we live in a world of personalization. This is e-commerce would not be possible today without that, because e-commerce inherently implies that these big giants, the Walmarts, the Amazons, they have an irrationally large number of items in their inventory. We are talking about 100 million items or something like that. When you have so many items, you can't really have a web page displaying them, even by categories. In any category, there would be a very, very large number of items, and there'll be way too many categories. So recommender systems are actually pretty crucial to the e-commerce world. A lot of people purchase things that they have been recommended, and that drives a lot of revenue and traffic. So that's that. For Netflix, of course, one of the big selling points was that they could tell users that you like this movie, they would watch it and they would actually find it useful to their liking. Right? So that's that. Now, that's a summary of what we did. Now I would like to move on to the lab part. Any questions before we move to the lab, guys? If anybody has a question, please ask me. Because
So Asif, so for the loss function for the boosting, so is there a function called like the boosting loss function?
the loss function is not usually specific to, well,
the method?
Yes and no. See, think about it. Regression has a well-defined loss function, right?
Yeah.
Which doesn't terribly depend on whether you're using a decision tree or you're using a linear regressor or polynomial regressor. It is y minus y hat square. It is the error term. To it, you can add further regularization terms, etc. For decision trees is the number of nodes. In gradient boosting, for example, the extra term that you add is the damping factor lambda. That's your hyperparameter to regularize it. So that is the loss function there. The loss function, likewise, you can write for classifier. Now, what happens is that the answer to that roughly is yes. In the theory, when you do gradient boosting, you can, once you write the loss function and you look at the residuals and you train your model on the residuals, there is the gradient of this some loss over residuals and so forth. There are a few bits of formula and a bit of mathematics unique to gradient boosting. I did not cover that because that will get us into all this business of gradients and so forth. There is a little bit of that, but if you have to look in broad strokes, your approach should be that yes, every algorithm has associated with it its specific loss functions, but one simple way to go around, at least at this level, is to know that for classifiers, the loss function would be the cross entropy plus some regularization term. And for regression, it would be some squared error plus some regularization term. Okay. And invariant of what algorithm you use, ultimately in broad strokes, this is it. Are we together? Now, when you do other boost and when you do, for example, gradient boosting, there are nuances and they affect the mathematics of it. Right? Like, for example, when you do decision tree, you go through a process. You don't directly, I mean, you do have a loss function, yes, that's true, that you're trying to minimize, but you also go about it using, entropy, the entropy and the information gain, or the Gini, the index value is changing, right? Where does it have the best split points and so forth. So those are the mechanics of it, the internal mechanics by which you bring down the loss. Right? You do have a loss function, and then you bring down those loss values. So for each algorithm, there'll be its own special bit of mathematics. Like for example, for support vectors, we saw how we wrote the constraints and how we wrote stuff in search for the maximal margin hyperplanes. So those things do remain. So yes, gradient boosting also has its own bit of mathematics.
Okay, yeah, no, that makes sense.
Yeah.
Thank you, sir.
Sure.
Asif,
Yeah,
because boosting is computationally intensive, is this a classifier that we use secondary to optimization from others, or can we just go straight to boosting right away?
Actually, XGBoost and this CatBoost, they're very fast actually. We'll see this in the lab now. Let's look at it in the lab. You'll realize that they are very, very fast. Having said that, see, remember gradient boosting, any boosting, it's a black box model. So the question remains, is it justified to use a black box model? Your approach should always be to dial up from simple interpretable models. If nothing else, they form a baseline. So let's take an example. Suppose you have a model, a simple interpretable model, and it gives you 94% accuracy, right? Or precision or recall or F1 score, whichever metric you care about. Now, let us say that the gradient boosting gives you 94.7% accuracy or the metric value, whichever metric you are pursuing. the question needs to be asked, should I use this black box model? And even if you don't, does it make sense to use the simpler model, at least for explainability, for interpretability? Right? To cross-check if in all the regions of the feature space, the predictions of the two model match. If they do match, you might still use, let's say, a black box model, boosting, bagging, random, all of this. But you may choose to use the more interpretable model when you're having a conversation with business to explain why certain things are happening, isn't it? So for example, if you're an entrepreneur trying to sell ice cream on the beach, if it can predict what the amount of ice cream you'll sell on the beach would be, the entrepreneur may be pleased that you made an accurate prediction. He has to buy, or she has to buy a finite amount of ice cream and not have it go waste or lose business, both ways. On the other hand, the entrepreneur will have this nagging question in her mind that what if the wind changes, right? Because weather predictions are not exact. So what if the temperature is a little bit higher? What if the weather changes? What factors really affected it? Another basic question is that if you have an interpretable model, you can ask, what should I do to increase my business? Do you see that? Isn't it? So interpretable models go a long way, much further than black box models. You use black box models by compromising on interpretability to a large extent. And when you do that, you lose a lot of value. Your approach should always be to start simply. And that's what I've been trying to do. If you notice that in this workshop, I have taken you and emphasized feature engineering and showed you that at least for the river data set, none of the black boxes beat feature engineering. Do you remember seeing that, guys? For the river and the flag, none of the black box models, random forest, support vector machines, boosting, we'll do boosting today and see. They don't beat it. They at most come close to it. So feature engineering, thoughtful feature engineering, still remains the gold standard, right? So keep that in mind. Never forget that there is a no free lunch theorem. So we will go back to our river dataset. Just to remind you, the river dataset was, what was it? Yes. The river dataset looked like, hang on, before I go here. Yeah. The river dataset is, visualize the dataset, yes. So if you look at this visualization, just as a reminder, this was our dataset. And with this data set, we call this inner region the river, and then this the sand. And that's the intuition we use to make progress with this. Now, as we went through this workshop, as we learned new algorithms, we tried to apply each of these algorithms to this data set. And it sort of was a reference point to see how these algorithms work. I hope by now you must have seen that with scikit-learn, for example, going from one algorithm to another from a pure lab perspective, from a pure code perspective, often was as simple as just changing the name of the classifier. You did not have to do much. Import the classifier and just use it. And we could do, because it's a nonlinear, we could do it using feature engineering and logistic regression itself, which is, just as a recap, this is it. You saw us do and you saw us do polynomial regression, classifier, logistic with polynomial terms. We did a more feature engineering approach. We did all of this. We did a plot of the river. We extracted the river. If you remember, we looked at the distance from the river. So this was the best. This was a gold standard. Because if you remember, the goodness of this model was, if you looked at how well this model was, the residuals were perfect if you did this approach. And our with this, when we got a perfect map of the river, and from there, when we did the feature extraction, this was our goal. We said, if we extract our features well, then we can build a very simple, in fact, one-dimensional logistic regression model. Nothing can be simpler. We transformed the problem to a very simple problem, which was a classifier in one dimension, the dimension being, or the feature being, distance from the center of the river. And when we did that, we got a confusion matrix that was pretty good. This is a good matrix, as you can see, off-diagonals are rather small. And the classification report said, we have a F1 score, on average, F1 score of 84 and 92%. And all things taken together, the 89% is what we came out with as the weighted average of all of these things. So weighted average of accuracy is 89%. Now, for one, we got, for sand, we got 92% accuracy. For river, water, we got 84% accuracy. And we got a pretty impressive AU ROC curve, area under ROC curve. Just as a recapitulation, what is the area under ROC curve? Should it be more or less, guys? Do we remember that?
Should be a lot
More,
of area.
Bigger.
Maximize.
We want this thing to write for a very small false positive rate. We want the true positive rate to achieve close to 1, isn't it? Because between true positive and false positive, there is always a trade-off. Okay? You want a very high true positive rate by giving up, by having a very small false positive rate. Are we together? So that is that. And so you want the area under ROC curve to be high. This is a report on how much misclassification we got. Then we started trying all the algorithms we learned in this course with their decision trees. Decision trees also gave us pretty good result, but not as good. A simpler decision tree, for example, gave us a weighted accuracy of only 77%, at 12% less accuracy. Not as good. Decision trees tend to fit hard. The area under ROC curve doesn't look so good. By the way, you guys can play with it. If you make your decision tree more complex, this results will improve, right? You can try that out. Play with the parameters of the model, the hyperparameters of the model. Right? Then when you visualize, then we went to random forest and we said, if we use a random forest, how would it look? When we tried with random forest, it turns out that random forest pretty much achieved almost as good a result as feature engineering. This one is not as good, a little bit worse, but give or take, it's pretty much gets close to it, gets a pretty good number. The area under ROC curve is pretty good. So between random forest and feature engineering, which one would you prefer?
Feature engineering.
Yes, because it's an interpretable model. So given two models which are equally good at prediction, you always pick the simpler model. Right? Then you do the feature importance. Obviously, X1 is more important because the whole waviness is along the X1 direction. Then they are both important. Then you tried support vector machines with the RBF kernel. When you do that, once again, you look at the accuracy report. It turns out that the SVM by default parameters didn't do very well. But I left this as an exercise for you that tune the SVM and see if you get better results. The hint was that it can do very well. It can do state-of-the-art results like other. But you will have to tune this. And so that was an exercise for you guys to learn to tune the SVM. Okay. Then you have the reports. By now you must be noticing that you're falling into a pattern irrespective of the classifier. Your model diagnostics remain the same. The methodology remains the same. Right? And the code for changing the classifier usually is not a big deal. This is the precision recall curve. By the way, this is the feature importance, the Shapley value that I talked about. So today, I'm sorry, I'm yawning today. I had to be up since 6 in the morning after sleeping at 2. So okay, here we go. XG boost. What does this stand for? XGB. Extreme Gradient Boost Classifier. Right? So this is pretty state of the art these days. This and Cat Boost. Notice something very interesting. It fit into the model with just 190 milliseconds, which is very, very fast. Not only fit to the model, it even did the prediction in that same amount of time. So obviously boosting, this XG boost, it doesn't eat up too much of your time. It is actually pretty fast. It got the job done. What is its accuracy here? Oh, look at this. This is also comparable to random forest, you know. It got this with same good accuracy. This here it missed a point, but pretty close to state of the art. You get good results with this. The ROC curve also looks very good. Very nice. But guys, do you notice something very interesting? After learning the whole theory of XG boost and gradient boosting and so forth, when it comes to the doing of it, this was pretty straightforward. Do you notice that? The only line different is this, the constructor. We are creating a XGB classifier, extreme gradient boost classifier, rather than a SVM or a random forest or so forth. Everything else remains the same. This is something very nice about scikit-learn and modern libraries. They help you interchange classifiers very transparently, very sort of easily. You can plug in different classifiers into your model and do that. Now, obviously, I haven't gone into all the complications here, namely the hyperparameter tuning and so on and so forth. That's where a lot of the grunt work remains. You know, once you get good results, then the business wants you to make the best possible model, which means that you sit down and you start doing the hyperparameter tuning. Or it used to be what you would do so one of the things I was leading to is we wouldn't have time in this workshop, but I'll be giving a session on something called automated machine learning, or maybe a day to it, or a 3-4 hour session. If you guys are in, maybe I'll have a sign up sheet for that. It would be 4-hour session. If you guys are interested, just register for it. If enough people register, I'll make it some very nominal fee, very trivial amount, like $30, $40 or something. We'll have 4-5 hours of it, or $20, $10, whatever, depending upon how many people register for it. And then we will learn about automated ML if anybody is interested in that. What it means these days is, see, now you have many algorithms, right? By now, if you just count on your fingers how many algorithms you have learned since ML 100 and ML 200 just for classification, you would have counted about many. Logistic regression directly, logistic regression with polynomial terms, linear discriminant analysis, quadratic discriminant analysis, decision trees, random forest, boosting, where you have XG boost and we'll do gradient boosting and cat boost, right? Support vector machines. How many did we count? Roughly about 10. Each of these things further has a need for regularization, isn't it? So you need to regularize the data, L1 regularization, L2 regularization, decision tree pruning, how well you prune in a decision tree, whether you use Gini, you use entropy, right? And so forth. There are many, many hyperparameters in all of these models. So not only do you have to pick the best model, you have to pick the best hyperparameter in each of these models. A k nearest neighbors, kernel k nearest neighbors, then what is the kernel, which kernel to use, what is the value of the k. So this process used to be very tedious. It is very tedious. And actually, when you do that session with me, I'll make you do one data set, one new problem, not this river, but some problem, more complex problem. And I will ask you guys to find, for each of the 10 algorithms, to find the best hyperparameter. By the time you're done with that, all 10, you would be pretty tired. It would be a long day, just for one data set. And then the whole point is that you will learn such things like grid search, randomized search, and so on and so forth for the best hyperparameters of the model, the model tuning part. And you will realize what the day-to-day life of a data scientist looks like. Even basic things help. Like, for example, the data imputation that you do when missing values are there. How do you impute data? What data you do? How do you take care of a class imbalance? Let's say you use mode or something to take care of that anomalies. Then how do you deal with scaling of the data? Do you use standard scaling, min-max scaling, robust scaling? What do you do? So there are many choices that you have to deal with. And it has been sort of a bane that if you are in this space, you try a lot of things. You use an army of people to do that. So there has been a body of research that sort of asked this question, that can we not do it in a more intelligent way? And people have been trying to do that. Let me see if I can give you guys a reference in case you don't have to come to my workshop, by the way. You can read the book on your own. Let me at least give you the idea of the book. Where is it? Machine learning, automated. There's a Murphy's Law. The books are usually under my nose till I try to find it. And the moment I try to find it, it is nowhere to be seen. I swear it is here. I just can't see it. Okay, so let me give you guys an idea of that book. By going to Amazon, you can try reading it on your own. Automated. There are very few books on this topic. Automated machine learning. Yes, to my knowledge, yeah. So practical automated machine learning, but this is focused on Microsoft. This is the book. This is a very good book, actually. Wow, this book is available free on Kindle. By all means, guys, go and get it. I didn't know that. Well, I learned something. Let me go get the free version. I think the PDF of this book is also available. This automated machine learning by Hatter. Somebody mentioned that the PDF is also available online. They have very graciously donated this, or made it available for everyone. LinkedIn book, automated ML.org. Yes, this is the book. I would strongly suggest you get this book. This is the whole field of neural architecture search and do you see that chapter, this hyperparameter optimization? It's a lovely field. It's a fast emerging world because, you know, this is insanity to be sitting there and tuning every model and then finding which model is the best for a problem. So there is quite a bit, the future is actually somewhere in here. So I will be giving a workshop, maybe one day, a workshop on this. I don't think it will be covered in 4 hours, but it's really a lovely field. It's something that most people are not aware of, unfortunately. Most people don't know that you can actually do all this and that there are libraries available that can help you do that. So we'll learn about that. The lab part of it we'll do in that particular workshop. But these are COVID days. These things, it's very hard to say if anything that we plan to do will actually happen. Anyway, so this is, you realize that you can do gradient boosting. Again, the accuracies are pretty state of the art. Notice that all of these complicated models, nonetheless, they don't beat feature engineering. At most, they come close to it, very close to it sometimes. But that's about it. This is the ROC curve for the XGBoost classifier. Code is exactly identical. Right? By now, guys, are you feeling that as I scroll down the page, it's beginning to look rather repetitive?
Yes.
Yeah, this is it. And in a way, it's the beauty of modern algorithms that a lot of the code you can recycle. Right? A lot of you can sort of templatize it and then just keep changing the algorithms and keep printing it out. So what I do, for example, in this is one of the things that some people do is they will create an array of classifiers and then just run through them in a loop to see which one gives you good results. And then they'll pick the best. I wouldn't exactly advise you that. Why would I not advise that to you guys? Um, could you give a reason for it? Why is it not a good idea to just run through all the classifiers in a loop and check their accuracy?
Is it like a difference between feature engineering and using AutoML or like
No, the reason
deep learning?
the default value, the default values of a classifier without any hyperparameter tuning is really not an indicator of how well that classifier will actually perform when you have really tuned it.
It's like apples and oranges
That is right. You're
before they're all ripe.
oranges, exactly. So, you know, this is a classic game people play. If you want to show that your product is much better than the competition, you will do a so-called performance benchmark. You will bring a highly tuned version of your product to the benchmark. And you will make sure that you will use the competitor's version with absolutely out of the box without tuning. And then you'll do a bake off and then you'll show, see, my product is so much better. Obviously, this is quite a game people play in the software industry. And there's something of that here. And then some people, of course, get unscrupulous. What they will do is they'll go to the competitor's product and turn on logging, tracing, and turn on all the things that will slow it down. And then in their own, they will have a highly optimized version, and then they'll do a bake-off. So while that is unscrupulous, here people end up doing essentially that inadvertently without realizing that they're doing it. Out of the box, none of these classifiers will give you state-of-the-art performance. There is a lot of lemon to be squeezed, juice to be squeezed from the lemon by tuning it, by hyperparameter tuning. So what you have to do is you have to do the most tuned version of each of the algorithms and then compare it. Right? Though you might say that, by looking at just zipping through all the classifiers with default, you'll get some sense of what are good candidates. Some people believe that. I'm actually skeptical of that. In general, I know that so much is gained by tuning the algorithm. So much is gained that it is not worth just blindly applying. So for example, look at the data set 2, which was a regression problem. Linear regression didn't work, but all we had to do is add polynomial terms and it worked, isn't it? And it worked like a charm after that. So it goes to show that you shouldn't ever try to automate unless you do it very intelligently. And this whole field of automated ML is about how to do it more intelligently, right? How to more intelligently find the best models and the best parameters of the model.
Are you saying that Asif then it does require somewhere human intelligence as well?
No, go ahead. Does it require human intelligence? No, actually.
In tuning at least those parameters.
It was true for so far. See, people did. See, you take one classifier, right? And it has certain hyperparameters. So you can do either a grid search or a randomized hyperparameter search. Yeah. And so, by the way, did I ever explain grid search and the randomized search?
No.
No, then maybe remind me that I must cover today. Huh? I must explain these things to you. So these are the classical approaches. The trouble is that if you have 10 parameters, you're looking into a 10-dimensional hyperparameters, you're looking into a 10-dimensional space to search for. Computationally, it is brutal. And these brute force searches are not the intelligent way to go about it. So there are two things you can do. People have said that use your human gut feeling, your understanding of the problem, and then let that guide your search. But recently there has been more to it. The approach that people take, there's a whole bit of mathematics and nice, lovely body of work that is emerging and rapidly expanding. It says, there is a more intelligent way to do two things, just hyperparameter tuning, you can say, but more than that, it is called neural architecture search. Let us find the best architectures, the best classifiers. Let's build it up from the ground up, in some sense, to solve the problem. So for example, one example that we'll use is after deep learning. If you look at the state-of-the-art COVID-net, see, as of this moment, AI is still not reached the level that it could be useful in a practical level for COVID detection because it lags behind in specificity compared to the biological methods, you know, the testing, the RT-PCR. RT-PCR is more or less the gold standard. The hope was that, and the AI community hoped that they would catch up. The problem is not that they can't, the mathematics is not there. The problem is that there isn't enough data to train the neural network. But one of the, so that is at this moment, from a practical perspective, we are not there yet. But if you look at COVID-net, for example, one of the things you will see is this thing. We have used automated machine learning to discover, use that along with human judgment, bringing together both to create a really good neural architecture. And when you look at that architecture, the first thing you see when you look at it is, oh goodness, nobody could have thought of this. Are we together? Nobody would have been able to think of the architecture just as it is. So that's the world we are entering. It's a very exciting topic. And in fact, when I do the deep neural network, I feel now that it is almost pointless to do it the old way that people have been doing the deep neural network. So it's an interesting experiment. I'll be doing it from the latest cutting edge research backwards. I'll first introduce cutting edge research, where we are in the state of the art, and from there, go back and build the foundations, rather than slowly build the foundations and then do some more and do some more, and we'll never reach the cutting edge, which is the traditional way you teach this field. But I want to, as an experiment, do the other way around. Let's see if it works. Anyway, so this is, by now you do, so this is for classification. Let us now try to do it for regression. Let's go back to our California housing data. Once again, you remember we are trying to predict the value of the house. We did a lot of pre-processing and so forth. So here I've used actually not just XGBoost, but also gradient boosting. Both of them come with in Python and in R. And cat boost, I didn't get time. I'll let you guys entertain yourself with it. You take boosting. Here is the boosting implementation. Let's see how much does it take to do boosting. By the way, boosting, XGBoost has one limitation. When you do one-hot encoding, you notice that your feature names have developed this less than sign and so forth. XGBoost will fail actually if you have any of the features with the special symbols, less than, greater than, comma, etc. It doesn't work. It expects alphanumeric and underscore. So one of the things you'll have to do, especially for it, is you notice me renaming ocean proximity less than 1 hour from ocean to just rename it to something else that doesn't have the special symbols. And once you do that, you do the normal train test split. You notice that there are no special characters in the names. Once you are there, then you do the same thing. So what did I do? It could have been linear regressive. Except for this one line change, there are no changes. You do the model fit. But note, guys, how many hyperparameters there are that you could have tuned. Do you see that? The more complex the algorithms, the more number of knobs that you can turn, the hyperparameters there are that you can play with. Right? By the way, learning rate, right? This is the lambda that we talked about in our notes. The dampening of the learning rate, how slowly you want to learn. And remember, one of the lessons we learned is that the slower you learn, sometimes the better. And how many trees are you growing one after the other sequentially? These many trees you're developing. So there are a lot of things to tune in all of this. But when it comes to predictions and everything, good. You notice that it makes 84%, 84.68% is the coefficient of determination, the R squared. How does that compare, let us say, to random forest? Let's go and see what happened in the random forest. Random forest was 83.66 and mean squared error was 0.05. And what do we have here? Same, but it's a little bit better. XGBoost is a little bit better. Yeah. Why it is? Because XGBoost tends to overfit the data even less than random forest. So if I had to guess what was the reason for that very tiny improvement, it could be this. Right? So how good is this model? Let's look at the residual plot. Residual plot looks pretty good. This is a normal distribution of the residuals, right? You don't see any pronounced heteroscedasticity. It looks pretty good. Your prediction versus error, they seem to have a good relationship, 45-degree more or less relationship. Feature importance, you can do the feature importance here. Again, these values are more or less the same as other ones, right? What other models form. There is another version of boosting that we can invoke, which is gradient boosting. So one thing you notice that when I build this model, XGBoost, it built itself in how much time? 404 milliseconds. On the other, it's a very simple problem, the California dataset. Whereas if you do it on with gradient boosting, it takes 50% more time. Not by far, but a little bit more time. Right? This is not really a clue that this is XGBoost is faster than gradient boosting, but it's not really a definitive proof. But it's sort of there. When you deal with more complex problem, I suppose it's a bit more pronounced. Right? Again, you have a lot of hyperparameters in the model that you have to play with. The prediction, oh, what do you notice? Remember, that was 0.84, right? With XGBoost, 84.68% was there. And here, what do you get? Compared to that, 84.68 becomes 78.8. So gradient boosting, the traditional gradient boosting is actually, at least without hyperparameter tuning, it is noticeably worse, right? And it takes a bit longer. Which is why, I mean, most people use XGBoost, CatBoost, and so forth. However, it does build a pretty good model. It is, you don't see any heteroscedasticity. You'll see normal distribution of the residuals. More or less 45-degree angle between the two. Feature importance using this yellow brick is here. And then remember the Shapley thing that I taught you about, the more sophisticated way of finding the interdependence and the feature importance. So this is it. And so that is it, guys. Today's lab is this. Now, the lesson here to learn is, do you notice that in a way the theory gets more interesting, but the labs, hopefully, once you have practiced this enough, I hope much of the machine learning labs now are beginning to feel simple. Are you guys feeling that it is simple, guys?
More so.
Yes.
Yes, like more repetitive now.
Repetitive, you know. So this is it. Repetition or practice brings speed. Once you have practiced these things enough, for you, it is just a marginal cost to pick up the new algorithm from a practice perspective. And very quickly, you can become productive at it. What you need is a methodology, guys. More than the algorithms, I've also taught you a systematic way to approach a problem. When you approach a problem in a more systematic way, you don't make mistakes, right? You're careful. Now, I invite you to go and look at the various notebooks that people have posted on these data sets and see whether we have done, on average, a much more careful analysis than most of those posted solutions or notebooks on Kaggle or whatever. I don't know if any one of you bothered to compare. You would realize that just being careful, you come out pretty far ahead of the average. You might not be the best, but you come out pretty far ahead of the average, isn't it, guys?
Yes.
Yes.
Let us do that. Let's go and verify. This is our notebook, right? With all these things there in this. Actually, I haven't done that. Let's do this exercise together. Kaggle. California dataset. I'm sure there must be Kaggle notebooks for that.
The data set is built in Colab also, Asif.
Oh, okay, it's built in. Yeah, that's right. It must be. It's a classic data set. House prices, house prices. This is it. 2 years. How many notebooks are there? 282. Okay, there we go. Let's look at a typical notebook. 157 notebooks have been posted. This seems to, okay, I'll just go to a Python one, hotness language, because here we have a Python solution. This seems to be the best voted one. This is Shapey. Complete tutorial for beginners. Let's go and look at this, the best one, and see how we are doing with respect to the best one. The goal. So by the way, guys, something noticeably, the first thing that strikes you is that this fellow has actually given an introduction, which is a positive sign. Most people just jump into the code. You should explain what you're doing. He's doing that. He's taking the city coordinates. By the way, remember we did the log transforms and things like that. Let us say if he does the log transforms, he doesn't have a table of content or titles or break it up into sections. 2 functions, Cleveland, Ohio, whatever. Is it California data set or which data set is it? Geospatial feature engineering on the California, right? Okay. We'll come to know when we visualize the data. Yeah. So he's visualizing the data. Let's see, how did we do for visualization? Did we do visualization? Do you guys remember, guys? Were we careful enough to do visualization? Here it is. I will take it. So we have a visualization. In fact, we have a interactive visualization. So we do have visualization. What else? We projected it onto the map as a scatter plot. This fellow seems to have done also a scatter plot. We have done this. So let's see what we missed. And that is a great way actually to learn by seeing what you have missed. Below is a graph showing the size and location of the cities. So this is the city location. So more of this. Feature engineering, length vector between districts. And so this is actually very good. Yeah, I remember this person doing that. Very impressive. He did an interesting feature engineering. He said what matters is distance to the nearest metropolis. Length of vectors between districts and nearest towns. So somebody has contributed this. But you notice this graph, it's pretty nice actually. He's telling you how far is a house from the downtown effectively of some sort. Or distance to the biggest city. What are the biggest cities in the Bay Area? It is, I suppose, San Francisco, San Jose, Los Angeles, and San Diego. Or those 4 cities they probably are taking. So this is a nice thing. We haven't done that. So it is something to learn from. We can do that. Then, actually, I remember seeing this notebook actually in the past at some point. So he has taken this data, which is very good actually. Then he has done a stratified shuffling, and then he has split the data. Now the question is, why that? Can anybody answer this question? I'll leave that as an exercise. That before you split the data, why has he done a stratified split of the data? Can anybody?
So that I guess so that your test will not have more of one city and less of the others.
Yeah, because data has imbalances, right? There may be more points from one than the other. So you don't want to take a split in which, let's say that all the data points that belong to a small town, they are only in the training data and not in the test data. Right? Or all some particular feature, let us say, all the points that belong to an island, Catalina Island, belong only to the training data but not the test data. Or to the test data but not the training data. That would be bad, right? So stratified sampling is good. So read about it, guys. Huh? That is it. Then the rest of it is label binary. We did it actually straightforwardly. We also have this. We have this. This, it's commented. Oh, and then he stops. That's about it. He uses XGBoost. Right? And so you notice that when he does XGBoost, you notice that his root mean squared numbers are huge. So one of the things he did not do while he did feature engineering, which is very good, because he did not use the simpler algorithms, the standard linear regressions, other variants of it. There is no feature engineering. So for example, he did not do the log transforms. This data set sort of calls for log transforms. This particular guy who's done a very good job seems to not have done that. Let's try the next guy. I will limit myself to Python here. Who is the next best? Explaining your model predicting. By the way, this fellow also has not done feature importances or Shapley values. This person has done Shapley values, it seems. Interpretable machine learning, obviously. And he's put in quite, where am I? I'm not able to scroll. Yeah. So this is it. View the data. You see, well, this graph certainly needs aesthetic improvement, but still pretty good training. So he has not done stratification, stratified sampling. He's done a straightforward. He's using randomized regression because his point is to show Shapley. Do we have these in our models, guys? In our notebook, do we have these?
Yes.
Yes, we have this. Shapley is important.
In yours.
Those of you who took my boot camp remember that we gave a whole day to interpretable ML, Lime and Shapley and all of that. So this is good. A short notebook, it is good. Which is the next one? Let's go back and try the next best. Complete tutorial for beginners. Let's try a luck here. Hello, Cadlers, there's that. Oh, we have this, obviously. The other notebooks didn't have this. Scatter plot leaves something to be said. Then, yeah, more of the scatter plots. We do have this, but we have a better version of this, I suppose. Let's go and see, do we have it or not? Yeah, you see that? We have these, much more sort of deep informative versions of these. But let's go and see what else is good. He's looking at this, and from this, what does he conclude? Well, I hope he concludes that we need a transformation, data cleaning. So this is the imputer. He does a null value imputation. I haven't taught you imputation, so we didn't do it in this particular data set, but this is
Can
again.
you dial up the size a little bit? It's very small, please.
Okay, let's see. So this is the imputer, missing value imputation. That I talked about it, but we didn't do it in the data. We can do the imputation. These things we have. The scaling of the data. Oh, that's it. So he hasn't done the modeling. Let's go back and try somebody who has done the modeling. Optimized modeling, 24 volts. Import data, missing value. He notices that there is a skew. Hopefully he's, see, sometimes you can just look at the pictures and tell how the person is thinking. Hopefully he notices a right skew and does something about it. Notices a lot of outliers and he computes the medians and so forth. Unique for median, total number. He's finding the median of all of these. Checking for null values, EDA, exploratory data analysis. Let's see what he does. Figures. He notices that there's this big pillar. Probably he'll remove that. Population versus housing, not terribly informative. Removing outliers, good. So he has actually decided to drop outliers, which is very good. Population is then. So in every dimension, he's removing outliers. And then this looks very similar to what we have. This is just the correlation matrix. This is the correlation matrix. Do we have that, guys? We have that. This is just the count plot, the box plots. Do we have the count plots, box plots, etc., guys? Here it is. So this is what we have. Do you see it, guys? We have this. So he also has this. Pre-processing, he does that. Normalizing the data. Do we normalize the data? He is using min-max scaler. We use the standard scaler. Cumulative variance curve. So he's doing a principal component analysis to figure out how many things matter. We haven't done it in our notebook because PCA, did we do PCA this time? We did it in ML100, right? So we haven't done it in ML200. So he's looking at the PCA values, which is good. Then modeling. So standard, he's doing a simple linear regression. Then he's doing the residual plot. This is not really, the way we do it is a little bit better. How do we do it, guys? Residual plots. Let's look at it.
Yellow brick.
Yellow bricks. We use that, which I would consider a little bit better. Linear regression. Here we go. We do the. Also, we do all of these log transforms, etc. Linear regression. It's a good notebook. It's a very good notebook. Though we seem to have done better in some areas. It's very good. So now he's doing stepwise regression. He's trying to eliminate features by that. By the way, guys, let me just warn you, don't ever use the stepwise, backward and forward feature subset selection. Remember, that's the one chapter of the book I never taught you. Because I believe those methods are fundamentally flawed. You should never use it. So he seems to be using it. He's regularizing, seeing if that makes a difference. And then what does he conclude? His elastic net is the regularization with L1 and L2, isn't it? We'll do regularization next time. Our next lab is that, reg. Then he's bringing in decision trees. And in the decision tree, he's coming to the conclusion. He's doing some hyperparameter tuning, parameters, yeah. Do you notice this, guys? This is what I was talking about. It is not parameter tuning. The right word should be hyperparameter tuning. These are the, how deep can you make the tree and so forth. This is a topic we'll cover in a moment after the break. With all of this, he's coming up with feature importances. Do we have feature importances? We have that. Random forest, etc. Actually, and then again for grid search. Yeah, so now he's using the right word, hyperparameters, tuning. The best feature, random forest, and so on and so forth. He's doing that. And that's about it. That's that. So guys, what do you feel? Have I trained you to a level at which you can write a very good notebook amongst that can stand on its own and be respectable? Do you feel that you have been trained to that level now?
Yes.
Yeah.
Yes, Asif.
Do that, guys. Machine learning, or this field of machine learning, people get very excited about the latest and greatest research papers. What is the latest breakthrough in transformers? What's the latest breakthrough in CNNs and so on and so forth? But when you actually deal with a business problem, when you deal with real scientific data, you will realize that you go slowly. You will observe that quite often the best researchers, they speak slowly, they think slowly, they're very careful and methodical. That is where the gem is. Great things are done when you do it carefully, methodically, and deeply. You don't rush through it. So don't rush. Magic is not in the fanciest algorithm. It is good to use fancy algorithm, but fancy algorithm in the hands of a disciplined scientist is far more effective. Do it like that. Any other notebook worth looking before we take a break? Maybe one more, let's take. End-to-end machine learning, 18. Let's try a luck with this. Introduction. And yes, we have these histograms, you got right. The EDA, the maps, the scatter plots, the pair plots, the correlation matrix, data pipeline, right? And model training, model tuning. No one seems to have done the log transforms, etc. of the data. I wonder why. Okay, so by now we are getting rather low in the list. Maybe we can try our luck with most votes. This in terms of language. I think we have already done that. All right, guys. So I will, that calls for a break. After the break, I'll explain what, hyperparameter tuning is and how do you do that? Would that be okay, guys? Or should I just finish it quickly and that would be the end of it?
No, I think
we can take a break.
All right, let's take a 15-20 minutes break. It is 8:31 by my clock here. Let us take a break. Pause recording. We are on record. So suppose you have an algorithm. Think of an algorithm, let's say, whether it is a kernel, a KNN, right? Or you are talking of SVM, or you're talking about a random forest, decision tree, boosting, gradient boosting, and its variants, XGBoost, even logistic regression, let's say. And I'm deliberately taking classifiers, but the same argument applies to regressors, right? So with all of these, there are many, many hyperparameters that you can choose, not to mention that how much regularization to bring in, right? Whether to use L1, L2, or whatever it is. For trees, how deep, how many nodes there are in the trees, and so forth. The learning rate for boosting. These are all hyperparameters. In a random forest, how many estimators to take, right? How many predictors or features do you want to give as a consideration at a split point in the tree, right? While building the tree. So how do you find the best value? Right. So there are many ways that people think about. One, this has become practically a staple diet of interviews. So people usually suggest the approach grid search. The only reason I'm mentioning it is what people expect you to answer. So if you ever ask this question, you should say that, see, we can do grid search and explain what grid search is, but do emphasize that there are actually better ways to do things. So what does grid search do? So suppose you have two hyperparameters. Let me just call it hyperparameter 1, let me just call it HP1, and hyperparameter 2. This can take on values, arbitrary many, and I'll just take a continuous variable, let us say. Okay? So, for example, let's take regularization. In regularization, you have the lambda, so suppose you do beta j, let's say square, a ridge regression. You have SSE plus this. So what is the lambda value you should take? In SVM, it is the C is equal to the how much of a budget do you want to take, right? And in an RBF, like when we take a RBF kernel, what is the gamma? All of these. So they can take any arbitrary real value. So how do you go search about them? So there are a few basic things that you can do. You first take hyperparameter 1. Let me just call it H1. And you choose an array of possible values. Right? So for example, if it is kernel, K, in the kernel, you could take 1, 2, 3, 4, all the way to whatever you think reasonable. Let us say 50 neighbors you can take. So let us say that you have another hyperparameter which can take values from 0 to infinity. So how do you go about it? So one thing you can do sometimes is you can go with 10 to the power, for example, the cost. In a SVM, you could take 10 to the power minus 4, 10 to the power minus 3, 10 to the power minus 2, 10 to the power minus 1, 1. And then maybe you can go to a few positive powers also, 10 to the power 1, 10 to the power 2. These are all possible values you to take. Huh? I'm just taking just two examples of a hyperparameter. Now you realize that if you do H1, Cartesian product H2, how many possible combinations are there? Let's say that these are 50 and these are 1, 2, 3, 4, 5, 6, 7. So you're looking at effectively 50 cross 7 combinations. Isn't it, guys? So quite often, the grid search approach essentially suggests that what you do is you take for H1, for let us say a value H1 in this value 1 to 50 for H2 in now this value, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, 1, 10, 100, let us say. You lay it out like this, 10, that will be sort of in the consistent, 10 to the minus 2, 10 to the minus 1, this is 10 to the 0. For each of these two combinations, you can build a model. You can do a model with H1 and H2 values, isn't it? You can build your classifier or your regressor with these two particular values. And then you look at the metric. Let us say that you're doing classification and what you care for is the accuracy, ACC, isn't it? So you can maintain a table which would say H1, H2, and the metric accuracy. You can maintain a table, and then what can you do at the end of running through the two for loops, right? You're essentially going through every point of the grid, because this Cartesian product is this grid, right? These are the H1 values, these are the H2 values. So at every single combination, a point, combination of these two, you will have a certain value there, right? And from this value, you will then pick the minima. Oh, sorry, maxima, the most accurate, let me just say, maxima. Maximum value, maximum accuracy. So on cross-validation, on validation set. So that would be your best combination of H1 and H2. Does that make sense, guys? It's a simple idea, isn't it? Take every possible combination of the parameter values, take some discrete values. That's why the word grid. Grid implies a discrete set of values. And when you take a discrete set of values and you go about searching for it, you'll find some good combination that is good. Now, one further thing that you could do is you could zoom in. Zoom in. So suppose you come to know that a K is equal to, so suppose you went in the beginning, K is equal to 1, 10, 20, something like that. And so suppose you zoom into 10. In the second round, zoom in means next what can you do? You can take values like 5, 6, or 6, 7, 7, 8, 9, 10. You can just look in the vicinity of this, 12, 13 maybe, plus minus 3, to see if instead of 10, any of the neighbors give you better value. In the same way, suppose you find out that the cost or whatever it is, the other H2, the best value was 1. So what can you do now? You can search in the vicinity of 1. Try out whether 0.7 is good, 0.8, 1, yeah, 1.2, like, 5, something like that. You can zoom in and try out local values till gradually you find the best value of H1 and H2, right? H1, H2, right? So you're basically, or in simple terms, you're trying to do argmax H1, H2 for the metric accuracy of the model. This is what you're trying to do. So it could be accuracy, recall, whatever it is, whatever metric that you want. Area under ROC curve. You can pick your metric and then you pick those values that are the best. This is called grid search. If you look at textbooks, they'll often mention about grid search. It is the answer that you're supposed to give in interviews, etc. But actually, it happens to be amongst the ways of doing it, perhaps one of the less efficient ways of finding the best hyperparameters. There's actually a better way, which surprisingly is when you have H1, H2, what you do is you don't do grid search actually. You take random combinations of them. Okay, so what you do is you take random values of H1, H2. Are we together? So suppose you want to do 100 for 100 search events. What you do is you randomly pick H1, H2 values. When you randomly pick, what happens is you actually have an advantage. Let us say that your H1, H2 form a rectangle, right? This is H1, this is H2. In a grid search, what happens is you end up picking values only along this, isn't it? This. And so how many grid points did we pick up? Let's say, let's take this count and we'll see how many we are talking about. So 1, 2, 3, 4, 5, 6. 1, 3, 4, 5, 6, 36. You have 36 values. Right? Now see what I'm going to do. If you go, so this is grid. Now from this, if I go to randomized, we'll take the same thing, but we do something different. We say that randomly pick, let me use something else, some other color. Randomly pick 36 values, 1, 2, let me randomly go sprinkle these values here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Do you notice some difference between these two graphs, guys? These two plots? If you look at how many, if you do randomized search and you ask how many H2 values did you sample? How many H2 values did you sample? You will realize that you sampled 36 values. And how many H1 values did you sample? Also 36, isn't it? Because when you project it down, when you project along each of the axes, you will have lots of values. All 36 values will be here because it's very unlikely that any of those values would overlap if you take random numbers. So you get a more uniform search, a richer search of the feature space. Let us say that your best value turned out to be around here. What can you do now? In the next round, you can just draw a circle and you can test for more values in the vicinity of this. So today we believe that randomized search, this is called randomized search for hyperparameter optimization.
Asif,
Yes.
this assumes there's no local minima, right?
That is true. See, unfortunately there are, and that's why I call these methods not to be the very best methods, but it certainly is better. See, unfortunately most people, they don't know hyperparameter tuning at all. They just go with vanilla values or random guesses. If they know hyperparameter tuning, the only thing they know is grid search because that's what they have been fed in the textbooks and so on, right? And it used to be true, but now we know that randomized searches are better, better than that, right? So you can do this and you can zoom in and in the randomized search also, zoom in and repeat. In this circle, again, do randomized search next to the best possible value. And ultimately, you'll find the best hyperparameter models. So these two are very popular. If you look at the code on the web, in the scikit literature and so forth, you'll often find grid search and randomized search often being used. Just now we saw a Kaggle notebook. I don't know if you noticed, it was a double for loop for two hyperparameters. It was basically this sort of a thing. Different values of the hyperparameter you were building a model. It was a regression model there looking at mean squared error, but the idea is the same. And what I'm telling you is that if you must do that, instead do randomized search. It's just a superior way of doing it. But now comes the state of the art these days, right? And this is where automated ML and these things come in. We have a way of systematically doing hyperparameter, or my spelling is terrible, hyperparameter optimization, hyperparameter optimization. The theory is a bit more involved. That's why I say that let's have a dedicated session for it, huh? In which I talk about how these things are done. These are non-trivial methods. These are not just, you know, the above two. Let me just say that the above two are the poor man's methods. They are very popular. Most people don't know anything beyond that. But there is actually a systematic way to optimize your hyperparameters. And we will do that at some point. Today is not the day because it's a much longer discussion. I just planned that idea that there's a systematic way to do hyperparameter search. And there's this whole world of neural, you know, neural search and so forth. We won't go there at this moment. But today what I would like to do in the last few minutes of this class is summarize what is it that we learned. So if you ask, what is it that we learned in this course? I would say the biggest thing, the number one thing is do your analysis thoughtfully. The more you think what you're doing, the better you'll do. This is it looks almost like a cliche or a trite statement to say that. So this is it, you know, if there is one message I wanted to give in ML200, the overarching message is be thoughtful in your analysis. If you are, you will always outshine. You'll create an outstanding notebook. Go slowly, go methodically, and more or less, you will get somewhere. Very, very definitively, you'll have a good analysis of the data. And it's quite a pleasure, you know, when you can start with any data and you know that you'll find every data has some story to tell, you know, something interesting to tell you about. And it's a journey and you enjoy that journey. You know, it's not a haphazard or a quick rush to build a model and then say we have done it. See, in coding, in normal software, there is a lot of ego or one-upmanship. Or one guy will say, oh, you took 1 week to do this problem. I did it in 1 day, or you know, in half a day or 2 hours and so forth. And at some phase, I suppose we all have indulged in this sort of a game, right? Because we think it is a measure of intellectual superiority to be able to finish a problem quicker. Maybe true for normal software development. Actually, it's not true even then. My basic rule to my team at least is write code as slowly as you can, because code takes not much time to write, but 10 years people will maintain the code. So every single bug will come and haunt people later on, or you later on. So it is much better to write code slowly, correctly, as far as possible, write the first time, buffer it up with unit tests, lots of testing, and things like that, documentation, etc. Now, in machine learning, it couldn't be truer. People who do machine learning are not here. The game is not to be fast. The game here is to have the most predictive model, the most high-performing model, the most interpretable model, a most useful model. Usefulness and speed have nothing to do with each other. You create good, useful models when you go slowly. Right? When you go slowly, almost surely you'll hit it. Whereas if you rush ahead, it's a, you know, luck of the draw. You might hit luckily once, and you may feel pretty good about it. Most of the time, you won't hit it. Right? If you look at the brightest people in the field, they're very thoughtful, slow people. They are not people who rush or have this ego thing that I did it in 10 minutes. Anyway, most of these data sets, large data sets and algorithms, when you apply, they will take hours and hours and days to run on the machine anyway. So where is the rush? You might write code in 5 minutes, but it will still take hours to run on the machine. Okay? So iterations are slow. You might as well, instead of doing a lot of useless iterations, you might as well be very thoughtful and do careful iteration. So that's the message.